The variation of life on our planet is truly phenomenal. Every shape, size, color, and type seems to be represented out there. It feels like the only things that connect them are difference and diversity. Yet, we know this is not the case. Their very existence, our very existence, hinges on a commonality that we all share, from geckos to the great whales. And this shared factor can easily be missed. It is a quirk of molecular scale that has made life possible on this planet and is the foundational principle of organic chemistry. Let me tell you more. This is ASU. We often describe carbon as the building blocks of living organisms. That is because the biomolecules like proteins, DNA, and carbohydrates that we talk and hear about are all carbon-based molecules. If you look at the structures of these biomolecules, you'll quickly see that the carbon atoms essentially serve as their backbone, where the carbons are bonded to one another in a chain-like fashion or in a form of a ring. But you may be wondering, what exactly makes carbon so special that allows it to be used this way? If you're a science fiction enthusiast, you may have thought about alternative life forms that are not carbon-based. A common example uses silicon, which is the element found directly below the carbon on the periodic table. There is a reason why silicon is directly compared to carbon, and it is because carbon and silicon are similar in the fact that their atoms have 4 valence electrons in their outer shell. This shared characteristic means that silicon can also make the same number of bonds that carbon can make to generate similar molecules. However, despite the fact that silicon can make the same number of bonds as carbon and is also about 135 times more abundant on our planet, we are not silicon-based organisms here on Earth. There are, of course, many different reasons as to why we are not silicon-based organisms, but one reason is that these two seemingly similar atoms actually differ in terms of their size. And although the difference may seem trivial in words, this issue of size greatly influences, for instance, the strengths of bonds that carbon and silicon can make, which then affects the type of molecules that we can generate with these atoms. The differences in size can be easily understood by simply looking at the number of electrons each atom owns, which differs for each element on the periodic table. The electrons reside in areas outside of the atom's nucleus that we call atomic orbitals, and as the number of electrons increases, this would mean that the number of atomic orbitals would have to increase too. Specific to our conversation, carbon has a total of 6 electrons, while silicon has a total of 14 electrons, which makes silicon comparatively larger than carbon. When larger atoms come together to form a bond, this will result in the formation of longer bonds, which can be more easily broken than shorter bonds, which are stronger. As a reference, the average bond energy for carbon-to-carbon single bond is 346 kilojoules per mole, while the bond between silicon atoms is 222 kilojoules per mole. Higher the bond energy, stronger the bond. So quantitatively, we can see that carbon-to-carbon bonds are stronger than bonds between silicon. But let's visualize this as a molecule. Take a look at the size difference between a 6-membered ring made up of carbon atoms on the left versus silicon atoms on the right, and see the obvious difference in the bond lengths between the atoms. Let's put this into a context with the common six-membered biomolecule found in nature, glucose, which serves as an important energy source for us living organisms. Again, if glucose is made up of silicon atoms, it would create a molecule filled with longer, weaker bonds that would break apart more easily than glucose molecule that we take for granted that are carbon-based. And remember, it wouldn't be just glucose molecules, your DNA structure, proteins, and fats would all be affected if carbon atoms did not serve as their foundation, and life as we know it here on Earth would certainly not exist the way it does now. So whether you're a whale, a wallaby, a stingray, or a sailfish, or even just a plain old human, you share more commonalities than you think. We all have the same basic building blocks, and they are determined by the particular characteristics of carbon and the molecules it can create. This was ASU. Thanks for watching.